Welcome back to the Deep Dive. Today, we're really getting into the weeds, pulling apart some dense research to give you the critical technical insights you need.
Yeah, we're moving past the usual headlines.
Exactly. Our mission here is to truly understand the architectural finesse that's driving some really interesting results in AI efficiency.
And today, our focus is squarely on a fascinating paper. Less is more. Recursive reasoning with tiny networks. We're going to do a pretty deep professional dive into the Tiny Recursive Model, or TRM.
Right.
The goal is to really dissect its architecture, look at its efficiency compared to what came before it, HRM, and understand what it means to get state-of-the-art results on really hard puzzle tasks with, well, incredibly small models.
And minimal is the key word here, especially given the context. We kind of have to start with what people are calling the LLM ceiling, right? Because this work directly challenges that whole idea that bigger is always better, that you need more and more parameters.
Absolutely. If you look at the current state-of-the-art large language models, the huge ones, billions, hundreds of billions of parameters, they actually fail pretty significantly, measurably even, on these hard reasoning and puzzle benchmarks.
It's a real paradox, isn't it?
It is. These models are phenomenal at language, retrieval, creative stuff, but give them a deterministic, logical challenge like a complex Sudoku, a tricky maze, or those ARC-AGI geometric puzzles.
They just fall over.
Often, yeah. They struggle or fail outright. And that's even when you throw sophisticated techniques at them, like chain of thought or huge amounts of test time compute.
We're talking results where these massive models, Deepseek R1, Gemini 2.5 Pro, they might score low single digits or sometimes literally 0% accuracy on the hardest versions of these tasks.
Exactly. Which suggests that just sheer scale doesn't automatically give you deep compositional reasoning.
Which perfectly sets the stage for TRM.
It does. The headline finding is that TRM gets dramatically better generalization on these exact same benchmarks. And it does it using a network that's between, 5 and 7 million parameters?
Which is just minuscule in comparison.
It's tiny. For our audience, that's less than 0.01% of the parameters of many of these big competing models. It really suggests that architecture, specifically this deep temporal recursion, might be a way around needing just massive structural complexity.
Okay, so to really appreciate TRM's simplicity and, frankly, its effectiveness, we need to understand the complexity it was built to replace. Let's unpack the foundation. The Hierarchical Reasoning Model, HRM. This was Wang et al.'s 2025 attempt at these kinds of recursive puzzles.
Right. HRM was definitely ambitious architecturally. Its core novelty was this idea of recursive hierarchical reasoning. It wasn't just one network. It was two separate small networks.
Two networks. Why two?
Well, they had $5 for low-frequency updates. Think of that as the slower background reasoning, the gradual progress, and then $5 for high-frequency updates, more about the immediate solution-focused steps. And these two networks would recursively work on two different latent features, zeroidal and zero.
Okay, so zeroidal and CRS were carrying different kinds of information through the process.
That was the idea. The motivation partly was apparently biological, based on theories about different timescales in brain processing. But the main technical driver was this mechanism called deep supervision.
Deep supervision, that sounds important.
It's key. It's what allows the model to reason over time. Basically, it reuses the outputs, the latent features and indoles from one step, as the input or initialization for the next forward pass.
Oh, okay, so it builds on its previous state.
Exactly. And it could do this for up to, I think, $116 supervision steps in their setup. This allows the latent state to be refined progressively over a really long sort of temporal horizon.
So this is where we get into this idea of effective depth versus just the number of layers, right? HRM itself used two 4-layer transformer architectures, total of 27 million parameters, which, isn't huge by today's standards, but not tiny either.
Structurally, yeah, 27 million. But effectively, through that recursion and the deep supervision, HRM achieved an effective depth they calculated as 384 layers.
Wow, 384. How did they get that number?
It's basically multiplying the factors. The internal layers, the number of internal recursion steps, which they called NALE, the number of external recursion steps, and then those NASA supervision steps. It shows it could reason over this massive temporal depth without needing the memory or compute of actually stacking hundreds of physical layers.
Okay, but let's look at how it actually ran, because this seems like where the complexity really bit. The paper mentions a specific execution pattern. 6 function evaluations in one pass.
Yeah, it was intricate. With their typical settings like 1 and 2 internal steps and 2 external cycles, a single forward pass involved running 505 H's 6 times in a specific sequence.
Okay, 6 calls. And that brings us right to the big theoretical issue, doesn't it? This reliance on the implicit function theorem, IFT, and this thing called the one-step gradient approximation.
Exactly. That's the architectural Achilles heel. To avoid the enormous memory cost of doing standard backpropagation through time BPTT across all those 16 supervision steps, I mean, you'd have to store everything.
Right, that would be huge.
So HRM made a big assumption. It assumed that the whole recursive process converges to a fixed point, a steady state where Gellery iteration basically stopped changing much between iterations. Let's call them Zeller and Zeller time.
Okay, so assume it settles down eventually. How does that help?
Well, if you assume convergence, the math for the gradient simplifies dramatically. You supposedly only need to backpropagate through the very last couple of function evaluations in that sequence of 6. The idea is you treat all the preceding steps as if they just produce this fixed point, and you don't need their gradients.
Right, that's a technique used in things like deep equilibrium models, right?
Precisely. It can be very powerful. But, and this is the crucial critique from the TRM paper, HRM's application of it seems flawed.
How so? Wait a minute. If the theory needs convergence, but you said it ran maybe 2 internal steps before applying the approximation, how could it possibly have converged?
That's exactly the point the TRM authors make. HRM, in practice, didn't iterate until it converged. It just ran a fixed small number of steps and then applied the IFT approximation anyway.
Uh-oh.
Yeah. And the TRM paper points out that even in the original HRM paper's own examples, where they maybe ran it longer for illustration, the residuals, the measure of how far you are from that fixed point, were still clearly non-zero. It just wasn't converging.
So if it wasn't converged, that one-step gradient approximation is, well, it's potentially wrong, isn't it? It's introducing errors into the training signal.
That's the strong suggestion. The model wasn't getting the true gradient information, which implies that whatever performance HRM did achieve was likely coming from the iterative refinement itself, not from any real fixed point dynamics. And this lack of theoretical grounding made the model potentially unstable, hard to optimize reliably.
Okay, theoretical issues aside, what about just the raw training cost?
Yeah.
You mentioned HRM had this adaptive computational time, ACT thing to speed things up.
It did. The idea was clever. Let the model stop early if it thinks it's already solved the puzzle. So instead of always running the full non-616 6 steps, it might average, say, less than 2 steps on Sudoku. That sounds good.
Right.
But the way they implemented ACT used a Q-learning objective. To calculate the necessary values for deciding whether to halt or continue, it actually required running another full forward pass, all 6 function evaluations again, just to compute the loss for that ACT decision.
Wait, so every single training step needed 2 full forward passes?
Yes. So even though ACT might reduce the average number of steps per example, it doubled the computational cost per training iteration. That's a massive bottleneck.
Okay, that's a significant hidden cost. And finally, you mentioned this biological interpretation for $5.05.
Right, the low frequency, high frequency thing. While maybe interesting, it made the model harder to analyze and simplify. It sort of baked in this assumption of necessary complexity, making it hard to ask, do we really need 2 separate networks? Is this hierarchy essential?
Or is it just the recursion that matters?
Exactly. And that's the question TRM set out to answer by basically stripping away everything that wasn't provably necessary. So, enter the Tiny Recursive Model, TRM. It represents this shift away from that complex, maybe biologically inspired hierarchy towards just functional simplicity. And it managed to address pretty much every one of those theoretical and computational issues we just discussed.
While boosting performance, which is the amazing part.
Right, while significantly boosting generalization, the structural change is just dramatic. HRM, 2 4-layer networks, 27 million parameters. TRM, just a single tiny network, only 2 layers.
2 layers. And how many parameters total?
Depends slightly on the task. For the attention-based version, it's 7 million parameters. For a specialized MLP version they use for Sudoku, it's even smaller, just 5 million.
Yeah, 5 or 7 million down from 27. That's a huge reduction.
Huge! But it keeps the core mechanism. Deep supervision, still up to 17 ties and 6 steps. What changes is the internal structure within each step. It's much cleaner. Algorithm 3 in the paper lays it out.
Okay, walk us through that flow. How does one step work in TRM?
It's basically a 2-phase process within each larger supervision step. First, it recursively updates the latent reasoning feature, which they just call Sevigallers. It does this 9 times, taking the inputs, the puzzle, the current guess for the solution a year, and the previous.
So it thinks 4 9 steps, updating civ.
Exactly. Then, in the n+1 internal step, it updates the actual proposed answer, $y. And importantly, this update only uses the current dollar and the final state of Ziller. It doesn't directly use the raw input $6 for this final answer refinement step.
Okay, none steps for reasoning, no a step for the answer. And you said this whole cycle runs multiple times.
Right. This whole null plus LUDs and F cycle runs 2 different nuller times without tracking gradients, just letting the state evolve. Then it runs one final cycle, the T cycle, with gradient tracking enabled.
Ah, okay. And they found optimal settings for these.
Yes, the paper found that T3 to L external cycles and 166 internal reasoning steps worked best. So the gradient is only calculated through that final block of $6 plus 177 large internal operations.
Which brings us back to the gradient calculation. You said HRM used the IFT approximation to avoid BPTT across all 16 steps. If TRM is calculating gradients through that final T3 cycle, each with NTTT digs also 6 steps, isn't that still a form of BPTT? Didn't they just reintroduce the memory problem?
That's a really critical question. And the answer lies in why it's called the Tiny Recursive Model. Yes, TRM does perform BPTT, but only over that limited, unrolled window, the final T dollars times plus 1 steps. In their best setting, that's $3 times 6 plus 1 equals 21 internal function evaluations.
Okay, 21 steps. Still seems like a lot to backprop through.
It would be for a huge network. But crucially, the network itself is only 2 layers and 7 million parameters. The memory required to store the activations for 21 steps of a tiny 7M parameter network is actually manageable. It's far, far less than the memory needed for even one forward pass of a massive multi-billion parameter LLM.
Ah, I see. They traded the structural complexity huge weight matrices for temporal depth with a tiny network. The small size makes the limited BPTT feasible.
Exactly. They made the gradient calculation practical again by shrinking the per step cost dramatically.
And the performance numbers seem to justify this fully tracked gradient, right?
Absolutely. The ablation studies are really clear on this. They forced TRM to use the old HRM-style one-step gradient approximation. On Sudoku Extreme, its accuracy was only 56.5%.
Okay, not great.
But when they switched to the full backpropagation through that final T23 learn and just 66 cycle, accuracy jumped to 87.4%.
Wow, that's definitive. It proves the gradient signal from the actual recursive path is essential. That fixed point shortcut was losing critical information.
Precisely. It confirms the hypothesis. The real learning signal is in the process of recursion, not in some assumed final state.
Okay, so they fixed the gradient issue. What about the latent features? HRM had Eulers and a CTOGO with that complex biological story.
Right.
TRM just uses Eulers.
Yeah, they threw out the biological rationale entirely and went for a purely functional interpretation. It's much simpler. The Eulers is now explicitly the embedded solution state. It's what gets passed to the final output layer to be decoded into the actual puzzle answer.
And Eulers
is the latent reasoning feature. Think of it as the auxiliary scratchpad or memory the model uses to guide the refinement of Euler.
But why do you need both? Couldn't Euler just encode everything, including the potential answer? Why separate them?
That's a great question, and the paper argues this two-feature structure is the necessary minimum. You have to keep passing the forward across the steps because it represents the current best guess for the answer you're trying to improve.
Okay, track the answer. Makes sense.
And you need Ziller because if you only passed Euler, the model would essentially forget how it arrived at that previous guess. Ziller acts like a memory trace, like a latent chain of thought. It encodes the history, the intermediate steps, the constraints considered. Without Ziller, the model would just be trying to refine the answer in a vacuum, without context from its own reasoning process.
So Euler is the answer and Ziller is the how, the reasoning path.
That's a good way to put it. And again, the ablation study strongly supports this.
Right, table 2.
Exactly. Using the optimal two features, Zeller gave that 87.4% accuracy. When they tried to add more complexity, like using multiple scales for Zeller, giving $1 plus 77 features, total performance actually dropped to 77.6%.
So more wasn't better there either.
And if they simplified too much, using only a single feature to try and hold everything, accuracy plummeted to 71.9%. It really seems like this YS structure hits a sweet spot. Structurally minimal, but functionally necessary for this kind of robust recursive reasoning.
Okay, section 3. This is where we get into those really surprising, almost counterintuitive architectural choices and scaling results that came out of the TRM experiments. These findings kind of challenge the standard LLM playbook where bigger is better.
Absolutely. The first big win for simplicity, as we touched on, was going from HRM's 2 networks, 5LLR FH2, 27M params, down to just one single network in TRM, 7M params. You raised the question earlier. How can one network handle two different jobs, updating the reasoning morale and updating the solution errors?
Right, it sounds like you need specialized parts, but they use the same weights for both.
The clever part is that the specialization isn't structural. It's dynamic based on the input. When the network is doing the Neville update, the reasoning step, it gets the puzzle input $6 plus the current yell and similar. But when it's doing the update, the solution refinement step, the input $6 is often left out, or the overall input signature changes.
Ah, so the network just learns to behave differently depending on what specific combination of inputs it sees.
Exactly. It learns context-dependent function. The single network figures out, okay, with this input pattern, I should update the reasoning state. With that pattern, I should refine the answer.
And getting rid of the second network didn't just save 20 million parameters, it actually improved performance. The paper shows 87.4% for the single network versus 82.4% if they tried TRM with two separate networks.
Yes. Which strongly suggests that the structural specialization in HRM was actually detrimental, likely causing overfitting. On these small, hard data sets, extra capacity can be a curse. Forcing one set of weights to learn both related tasks seems to enforce more generalized, robust internal representation.
Okay, simpler structure, better generalization, that makes sense. But now for the really weird one, the optimal depth. Standard scaling laws for deep learning say more layers, more power, more abstraction. TRM found the complete opposite.
This is probably the most profound finding here, especially for designing specialized systems.
Yeah.
The authors deliberately tried increasing the TRM network back to 4 layers, matching HRM's depth. What happened?
Performance dropped.
Right. The 4-layer TRM only got 79.5% accuracy, but shrinking it down to just 2 layers pushed performance up to the peak of 87.4%.
So why? Why would adding layers, increasing the model's potential capacity, actually hurt performance on these tasks?
Overfitting, again, but specifically structural overfitting. On small data sets like Sudoku Extreme or Maze Hard, giving the model more layers, more static depth, just gives it more capacity to memorize specific training examples or spurious patterns. It learns the instances rather than the underlying rules or reasoning process. But by using a tiny 2-layer network and forcing it to iterate many times, incurse internal steps, you restrict its ability to just memorize. It has to reuse that small set of weights over and over across time. This seems to mitigate overfitting by limiting the static parameter space and forcing the model to find a solution through temporal depth and iterative refinement instead.
So they deliberately traded static structural capacity for dynamic recursive capacity.
That's the core idea. It's a fundamentally different way to think about model capacity for these kinds of problems.
Fascinating. Okay, let's move on to how they streamlined that adaptive computation time, the ACT mechanism.
Right. We established HRM's ACT was clever but computationally costly because of that second forward pass needed for the Q-learning objective. TRM got rid of that completely.
How do they manage early halting then, without the Q-learning?
They radically simplified the objective. They ditched the whole predict the value of continuing part of Q-learning. Instead, they just used a simple binary cross-entropy or BCE loss on the probability of halting. And that probability is basically conditioned only on whether the model thinks it has reached the correct final solution.
Ah, so it just learns. If I'm confident I have the right answer, output a high probability to halt. Much simpler.
Much simpler. And critically, this BCE loss can be calculated within the single forward pass. No need for that expensive second run. They removed a major training bottleneck.
And did simplifying ACT hurt performance?
Nope. The results were almost identical, 86.1% accuracy with the simple BCE-based ACT versus 87.4% when just running the full fixed number of steps. So they gained significant training speed, essentially for free, without sacrificing generalization.
Okay, another win for simplification.
Yeah.
Now let's talk about attention versus MLPs. This was another surprise. We usually think of attention as the go-to mechanism for sequence or spatial data, but TRM found a case where plain old MLPs were better.
Yeah, this again boils down to matching the model's inductive bias to the specific problem geometry and, crucially, the context length. For tasks like Sudoku, you have a small, fixed grid 9x9. The number of input tokens, dollars, is relatively small compared to the feature dimension.
Right, 81 input patches or tokens.
In that scenario, the global computation of self-attention, where every token attends to every other token, might actually be overkill. It introduces a lot of parameters in computation that might not be necessary for capturing the primarily local constraints of Sudoku.
And the performance difference was huge here, right? The paper shows standard self-attention only got 74.7% on Sudoku Extreme.
But when they swapped out the self-attention block for a simple MLP block, something akin to the MLP mixer architecture, which focuses more on mixing features across channels locally rather than global token interaction performance, shot up to that optimal 87.4%.
Wow. So for small fixed grids, the simpler MLP was just a better fit.
It seems so. It provided a better inductive bias for that specific data structure, removing unnecessary complexity.
But it's crucial to add the caveat. This only worked for the small context tasks.
Absolutely critical caveat. When they moved to tasks with much larger grids, like Maze Hard or ARC-AGI, which use 30 by 30 grids, suddenly you need that long-range spatial reasoning capability.
And attention becomes necessary again.
Exactly. For those larger context lengths, self-attention remained the superior inductive bias. You need that ability to relate distant parts of the grid. So the lesson is, tailor the architecture, even the basic layer type, to the geometric constraints of your specific problem.
Makes sense. One final architectural piece. Training stability and the use of IME.
Right, exponential moving average of the weights. This turned out to be surprisingly important. When you're training these very small networks, especially on potentially small or specialized data sets, the training dynamics can be quite sensitive. The model can easily fall into sharp local minima or even diverge catastrophically.
So IME helps smooth things out.
Precisely. By maintaining a moving average of the model's weights, they used a decay factor of 0.999, so it's mostly based on recent history. It dampens sharp oscillations in the parametered updates. It acts like a regularization technique, promoting smoother convergence to better, more generalizable solutions.
And this wasn't just a minor tweak, it significantly impacted the final result.
It really did, according to the paper. Without IME, the best they could get on Sudoku Extreme was around 79.9%. Turning on IME pushed it up to the final 87.4%. It highlights that when you minimize the architecture structurally, you often need to maximize the robustness of the training process itself. All right, so we've dissected the architecture, the simplifications, the counterintuitive findings. Now let's tie it all back to the actual benchmark numbers, really emphasizing that scale difference. We're comparing a tiny 5 to 7 million parameter model against giants.
Okay, let's start with the pure puzzle benchmarks, where we said traditional LMs often just get 0. Sudoku Extreme.
Right. TRM MLP, the 5 million parameter version optimized for Sudoku, achieved 87.4% accuracy. Now, compare that. Its direct predecessor, HRM, with 27 million parameters, only managed 55.0%.
It's over 30 points higher with what, less than a fifth of the parameters?
Exactly. And direct prediction LLMs, often 0.0% on this specific extreme variant because they just can't handle the complex iterative constraint satisfaction needed. So yeah, a massive leap over the prior specialized state-of-the-art.
Okay, what about Maze Hard? This one needs the attention mechanism, so it's a 7 million parameter TRM app.
Correct. And the story is similar. TRM ad achieved 85.3% accuracy on Maze Hard. HRM, again at 27 million parameters, was significantly lower at 74.5%. The simplified architecture and the full back propagation just proved more effective at navigating these large, complex 30 by 30 mazes.
So clear wins on the pure puzzles. Now moving to the ARC-AGI benchmarks. These are seen as tougher tests, probing more general visual and geometric reasoning. How did TRM do on ARC-AGI 1?
On ARC-AGI 1, TRM attention's 7 mperms reached 44.6% accuracy. Again, this surpasses HRM, which got 40.3%. What's really interesting here is comparing it to the big guns.
Right, like Gemini.
Yeah, the paper cites Gemini 2.5 Pro, using a huge 32K context window to try and process the examples in the query, only achieving 37.0%. Now, sure, there might be other, even more specialized models purpose-built just for ARC that score higher, but the fact that this tiny, relatively simple recursive network is competitive, even outperforming a massive generalist model, is quite remarkable.
It really is. Okay, and then there's ARC-AGI 2, which is notoriously difficult.
Extremely difficult. Here, TRM got 7.8% accuracy. Now, 7.8% might not sound amazing in absolute terms, but context is everything.
What do the others get?
HRM only managed 5.0% and Gemini 2.5 Pro 4.9%. So even on this incredibly challenging benchmark, TRM shows a substantial relative improvement over both its predecessor and a state-of-the-art LLM. The pattern holds across all 4 domains.
Simpler, smaller, fully backpropagated recursion just generalizes better on these specific tasks.
That's the consistent finding. It beats the more complex HRM, and it absolutely crushes non-recursive massive LLMs that try to solve these through direct prediction or less structured reasoning, like basic say TOT.
So the bottom line on efficiency is just Undeniable. State-of-the-art results on hard reasoning tasks with 5 to 7 million parameters. It feels like it fundamentally changes the equation for building systems for these kinds of problems.
It really does challenge the scale is all you need narrative, at least for these domains. And just to recap that winning recipe they landed on, it was that single two-layer network pushing the dynamic depth with ONI 1666 internal recursions and 2T33 external cycles for the gradient calculation within the non-up 16 down 6 total supervision steps using AtomW, and crucially, stabilized by that EMA setting of 0.999.
Optimized for iterative depth, not static width or depth.
That seems to be the key insight. They found where structural complexity started hurting and leaned entirely into making the recursive process as effective and stable as possible. Hashtag Shack outro.
Okay, so stepping back from all the technical details, what's the big picture takeaway here? For me, it's that TRM provides really compelling evidence that you don't necessarily need massive complexity, you don't need astronomical parameter counts to get top-tier performance on certain types of hard reasoning tasks.
Right.
What you do need seems to be the right architectural prior, in this case, a robust, simple recursive mechanism, combined with actually tracking the full gradient information through that process.
And the paper's conclusion really hammers this home. TRM is explicitly simpler than HRM. It gets rid of that questionable reliance on the fixed point theorem. It doesn't need fuzzy biological justifications. It uses drastically fewer parameters. It simplifies training by removing that costly second forward pass for ACT. And despite all that simplification, or maybe because of it, it consistently generalizes better.
It really feels like a case study in Occam's razor for network architecture.
It does. And this work naturally opens up some really interesting questions for future research.
Like the big one. Why exactly does this deep recursion with a tiny network work so much better than just building a bigger, deeper traditional network for these problems?
Exactly. The authors suspect it's about mitigating overfitting on these smaller, constrained data sets, but we lack a solid mathematical theory for it. We need proper scaling laws to understand how to best set these parameters, the layers, the not toler, the $2 for different kinds of problems. Right now, finding that sweet spot of 2 layers, $106, $2, $3, feels a bit empirical.
Right, we need the predictive theory. And another thing is that TRM, like HRM, is still fundamentally a deterministic prediction model, right? It outputs one single answer.
Correct. It's supervised to predict a specific target output. A huge next step would be to figure out how to extend this kind of efficient recursive reasoning into a generative framework.
So it can handle problems with multiple possible valid solutions.
Exactly. That would broaden its applicability significantly beyond just these single-answer puzzle domains.
Okay, so that brings us to our final provocative thought for you, our listeners, to chew on. Given these findings that you can achieve this kind of deep, complex reasoning by iterating a tiny, say, 7 million parameter network, does this suggest that maybe the huge industry focus on just scaling up the depth and width of general-purpose transformers, Mike? No, maybe not the most efficient path forward for certain high-value, specialized reasoning tasks.
Should we perhaps be putting more effort into architecting efficient temporal recursion rather than just building ever larger static structures? It's definitely something to consider, especially when thinking about the economics and the sheer resources involved in training and deploying massive models versus potentially a much smaller, specialized recursive ones.
A fascinating thought indeed. Thank you for joining us for this deep dive into the world of tiny, powerful recursive models.